this lecture, I am going to present what is continuous beam, what are the step-by-step procedures to solve the continuous beam by three-moment theorem. Then I would like to solve two problems. First problem, when one end is simply supported and other end is overhanging. And second problem, one end fixed and other end overhanging. Then what is continuous beam? A beam which is supported on more than two supports or more than one span is called continuous beam. Such a beam, when loaded, deflect in the form of a curve such that at the intermediate supports the slope of elastic curve for the two spans will be the same. At the intermediate supports there will be the bending moment. If the end supports is simply supported, the bending moment there will be 0. When the end is fixed, there will be the fixed end moments and the slope at the fixed end will be 0. And the moment of inertia of beam in different spans may be same or different. Then coming to what are the step-by-step procedures to solve the continuous beam. The Clapeyron theorem of three moments can be used to analyze the two consecutive span of continuous beam. First, assume each span of beam as simply supported. Then find the free bending moment by using the standard formula. Then draw the free bending moment diagram of two consecutive span. Then find the area of free BMD A1, A2 and CG distance of the area from both ends support, that is small a1 and small a2. Then identify the support moments which are to be determined with MA, MB and MC. Then use Clapeyron theorem of three moments for two consecutive span and find the value of unknowns. If the beam is of non-uniform section, that is EI is not constant and no settlement of supports, so that case the Clapeyron theorem of three moments MA into L1 by I1 plus 2MB L1 by I1 plus L2 by I2 plus MC L2 by I2 is equal to minus 6 capital A1 small a1 by I1 L1 minus 6 capital A2 small a2 by I2 L2. So this is the Clapeyron theorem of three moments when the beam is of non-uniform section and no settlement of support. And if the beam is of uniform section, that is EI is constant and no settlement of support, so that case the Clapeyron theorem of three moment reduces to MA L1 plus 2MB L1 plus L2 plus MC L2 is equal to minus 6 capital A1 small a1 by L1 minus 6 capital A2 small a2 by L2. So this is the Clapeyron theorem of three moments. If the beam is of non-uniform section and if the beam is of uniform section. The solution of the equation gives the value of the support moments. Then draw the final bending moment diagram after getting the unknown support moments. Overlap both free bending moment diagram and support moment bending moment diagram. Then after cancelling the overlapping portion, the rest diagram is the final bending moment diagram. Then find the support reaction of continuous beam by analyzing individually span by taking both load and moments. Then after knowing the reactions, find the shear force value at each support and at different positions. Then draw the shear force diagram of a continuous beam. Then coming to the first problem, a continuous beam ABCD is simply supported at A and continuous over spans B and C. The span AB is 6 meter and BC is 6 meter respectively. An overhanging CD is of 1 meter length. A concentrated load of 20 kilonewton is acting at 4 meters from support A. An uniformly distributed load of 10 kilonewton by meter is acting on the span BC. A concentrated load of 10 kilonewton is acting at D. So this is the continuous beam, and here the support A is simply supported and CD is overhanging, and span AB of length 6 meter, span BC of length 6 meter, and CD overhanging 1 meter. One concentrated load of 20 kilonewton which is acting at a distance of 4 meters from the support A. A uniform distributed load of 10 kilonewton by meter is acting on the span BC throughout the length, and a concentrated load of 10 kilonewton which is acting at the end D, and the moment of inertia of span AB is given I, and the moment of inertia of span BC is given 2I. So in this problem, find the support moments by using the 3 moment of theorems, then draw the bending moment diagram, then draw the shear force diagram. First, apply the Clapeyron theorem of 3 moment to the span AB and BC, 2 consecutive span. Draw the free bending moment diagram by treating each span as a simply supported beam. So first you have to draw the free bending moment diagram or simply supported bending moment diagram. So for free bending moment diagram, for AB is a triangle, because on span AB there is having the eccentrical loading 20 kilonewton, that is at a distance 4 meter from the support A and 2 meter from the support B. The free bending moment diagram for AB is a triangle with maximum ordinate under the load, that is 20 into 4 into 2 by 6 is equal to 26.7 kilonewton meter. Then on the span BC there is having the uniform distributed load. So due to this UDL, the bending moment diagram is parabolic. Then the maximum ordinate that will be obtained at the midpoint of the span BC. So the free bending moment diagram for BC is a parabola with maximum ordinate at midpoint, and this is equal to 10 into 6 square by 8 is equal to 45 kilonewton meter. Due to simply supported end, the moment at A is 0 and the moment at B is equal to mb, and the moment at C that you can find out by taking this portion as a overhanging portion. So you have to treat this portion as a cantilever, and due to this 10 kilonewton load, so you have to find out what is the bending moment at the support C. So mc is equal to minus 10 into 1, that is minus 10 kilonewton meter. So the moment at A is equal to 0 and moment at B is equal to mb, and moment at C is equal to minus 10 into 1, that is equal to minus 10 kilonewton meter. Then apply 3 moment theorem to the span AB and BC, that is MA L1 by I1 plus 2MB L1 by I1 plus L2 by I2 plus MC L2 by I2 is equal to minus 6 capital A1 small a1 by I1 L1 minus 6 capital A2 small a2 by I2 L2. So this is the free bending moment diagram for span AB and span BC. The maximum ordinate 26.7 kilonewton meter at the loaded point, and here the maximum ordinate 45 kilonewton meter at the midpoint of the span BC. So this is triangular and this is the parabolic. So the area of this triangle is equal to half into base into height. So here the base is given 6 meter and the height 26.7. So the area of this free BMD capital A1 is equal to half into 6 into 26.7, that is equal to 80.1 kilonewton meter square. Similarly, the area of the free BMD for the span BC, that is equal to A2, So A2 is equal to 2/3 into base into height. 2/3 into 6 into 45, this is equal to 180 kilonewton meter square. Then the central distance of the area A1 from the left support, that is small a1, is equal to 6 plus 4 by 3, that is equal to 10 by 3, is equal to 3.33 meter. Similarly, the central distance of area A2, that is small a2, that is you have to take from the right support C, and this A2 is equal to 3 meter. Then the length L1 is equal to 6 meter and L2 is equal to 6 meter, and I1 is equal to I and I2 is equal to 2I. Then apply these values in Clapeyron theorem of 3 moments. So, that is MA 6 by I plus 2MB 6 by I plus 6 by 2I plus MC 6 by 2I is equal to minus 6 80.1 into 3.33 divided by I into 6 minus 6 into 180 into 3 by 2I into 6. Then after simplification, MB is equal to minus 28.15 kilonewton meter. Then you can draw the final bending moment diagram. So here you got 28.15 kilonewton meter, that is at the intermediate support B, the moment, and at the support A the moment is 0, and at the support C the moment is 10, and this is the bending moment diagram due to the support moment, and this is the bending moment diagram due to the load which is acting on the continuous beam. Overlapping the free bending moment diagram and the support moment bending moment diagram. So here the positive negative, this portion is cancel each other, and this portion is also cancel each other due to positive negative. So here the net final bending moment diagram, this is positive, this is negative, this is positive, and this is negative. Then you can find out what is the moment here at the midpoint of the span BC, and what is the moment for span AB at the loaded point. So that you can find out by taking the similar triangle, because here you know this is, you have to take, this is one triangle and this is another triangle, and take this ordinate is x, and you know this ordinate is 28.15. 28.15 divided by 6 is equal to x divided by 4. Then you can find out what is the ordinate, this one. Then you know this total ordinate is 26.7 kilonewton meter. Then after deducting this x value, so you can find out the maximum, the positive moment just below the load point, that is equal to 7.94 kilonewton meter. Similarly, here also you can find out at the midpoint of the BC, the bending moment you can find out by taking the similar triangle, because you know this total ordinate is 28.15 and here this ordinate is 10 kilonewton meter. So this ordinate is 18.15, and take this ordinate is y. So here you take, this is one triangle and this is another triangle, and take two similar triangle and find out the ordinate y. So 18.15 divided by 6 is equal to y by 3, this one. So you can find out y is equal to 9.075. So after knowing the y value here, so you know the total ordinate here is equal to 45 kilonewton meter, and you have y is equal to 9.075 kilonewton meter, and you know this ordinate is equal to 10 kilonewton meter. So this is free bending moment diagram, and this is the support moment bending moment diagram. So this is 45 minus 9.075 minus 10 is equal to 25.925 kilonewton meter. The positive moment at the midpoint of span BC is equal to 25.925 kilonewton meter, and the maximum value, the maximum moment that you can find out where the shear force is 0. So after plotting the shear force diagram, so you have to find out that the zero shear force position and at that position you get the maximum bending moment. Then find out the reaction by taking the load and the moment separately for the individual span. So for span AB, so this is the load is given and the moment you got, this is 28.15 kilonewton meter. Similarly for span BCD, so here you have to take the UDL 10 kilonewton by meter, that is on the span BC, and there is having one point load at the end of the beam, that is at D point, that is 10 kilonewton, and here the moment you got, that is 28.15 kilonewton meter. Then you find out what is the reaction. For span AP you have to find out RA and RB1, and for span BCD you have to find out RB2 and RC. Then after knowing the RB1 and RB2, then you can find out, so the total reaction at the support B. The total reaction at support B is equal to RB, that is equal to RB1 plus RB2. So let us come to the span AB by taking the moment about the support B. So you have to find out what is the reaction at A. Then after knowing this reaction, so you have to take the summation of vertical force is equal to 0. Then you can find out what is the reaction at B, RB1. So first you take the moment about B and find out reaction at A. That is RA into 6 plus 28.15 is equal to 20 into 2. RA into 6, this is rotating clockwise direction, and here the moment is also given clockwise. So RA into 6 plus 28.15, and due to this load the moment is anti-clockwise, 20 into 2 is equal to 20 into 2. Then RA is equal to 1.975 kilonewton. Then you know the summation of vertical force is equal to 0. This is the equilibrium equation. So here the upward force is equal to downward force. The upward force is equal to RA plus RB1, and the downward force is equal to 20 kilonewton. So RA plus RB1 is equal to 20, then RB1 is equal to 20 minus 1.975, this is equal to 18.025 kilonewton. Then RB1 is equal to 18.025 kilonewton. Then let us take the span BCD and find out the reaction RB2 and RC. So here also you have to take the moment about the support B and find out what is the reaction at the C. Then take the summation of vertical force is equal to 0, and from that equilibrium equation you can find out what is the reaction at the support B, RB2. So taking moment about B, RC into 6, this is anti-clockwise rotation, and here this is also anti-clockwise moment plus 28.15, and due to this UDL the moment is clockwise direction, 10 into 6 into 3, and due to this load the moment is clockwise direction, 10 into 7. So from this equation you get the reaction at C, RC is equal to 36.975 kilonewton. Then take the summation of vertical force is equal to 0. The total upward force is equal to the total downward force. The total upward force is equal to RB2 plus RC, and total downward force is equal to 10 into 6 plus 10. Then find out what is the reaction at support B, RB2. RB2 is equal to 70 minus 36.975, this is equal to 33.025 kilonewton. Then RB2 is equal to 33.025 kilonewton. Then after getting the RB1 and RB2, you can find out the total reaction at B, that is equal to RB is equal to RB1 plus RB2. RB1 is equal to 18.025 and RB2 is equal to 33.025. So the total reaction at B is equal to 51.05 kilonewton. Then find out the shear force at different position. So the shear force at D, that is right side downward force, that is positive. So shear force at D is equal to 10 kilonewton. Shear force at D is equal to FD, that is equal to 10 kilonewton. Then shear force just right of C, so this is remain constant. Shear force just right of C, FRC is equal to plus 10 kilonewton. Then take shear for just left side of C. So here this is the upward reaction. So minus RC. So shear force just left of C, FLC is equal to 10 minus 36.975. So this is equal to minus 26.975 kilonewton left of C. Then shear force just right of B. So here you have to take this UTL 10 into 6 plus 10 into 6. Shear force just right of B minus 26.975 plus 6 into 10. So this is equal to plus 33.025 kilonewton. Then shear force just left side of B. So here you have to take the upward reaction, that is negative. So this is 51.05. So shear force just left of B, FLB is equal to 33.025 minus 51.05. This is equal to minus 18.025 kilonewton. Then shear force just right of E remain constant. FRE is equal to minus 18.025 kilonewton. Then shear force just left of E. So you have to include this load. This is downward force. So this is positive. FLE is equal to minus 18.025 plus 20. This is equal to 1.975 kilonewton. Then shear force at A is equal to 1.975 kilonewton. That is equal to RA. So here you know RA is equal to 1.975 kilonewton. So shear force at A, FA is equal to 1.975 kilonewton. Then you can draw the shear force diagram. So shear force at D 10 kilonewton, shear force just right of C 10 kilonewton, shear force just left of C minus 26.975 kilonewton. So you have to draw this is downward direction. Then shear force just right of B, this is plus 33.025 kilonewton. So this is linear, the load is UTL. So this line is linear. That is, you have to join from 26.975 negative to 33.025 positive. Shear force just left of B. So here this is minus 18.025 kilonewton. So this is downward. And shear force just right of E constant 18.025 kilonewton. Then shear force just left of E. So here this is plus 1.975 kilonewton. And shear force at A, this is 1.975 kilonewton. So this is the shear force diagram. On the span BC, here the shear force change its sign. So at this position, you get the maximum bending moment. Here you have to find out this distance by taking the two similar triangle. So you can find out what is this distance. So here the total length is your 6. So let us take this length is your x. So this length is equal to 6 minus x. So 33.025 divided by 6 minus x is equal to 26.975 divided by x. So from this relation you get the zero shear force position, and after knowing the zero shear force position, so you can find out what is the maximum positive bending moment on the span BC. So this is all about the analysis of the continuous beam when one end is simply supported and the other end is overhanging. Then coming to the second question, a continuous beam ABCD is of uniform section. It is fixed at A, simply supported at B and C, and CD is an overhanging. AB is equal to BC is equal to 5 meter and CD is equal to 2 meter. If a concentrated load of 30 kilonewton acts at D, determine the moments and reactions at A, B and C, then sketch the shear force and bending moment diagram and mark in the salient values. So here this is the continuous beam, and here the support A is fixed and support B is the intermediate support and CD is the overhanging portion, and one load is present at the point D, that is 30 kilonewton at a distance 2 meter from the support C. So here you have to take this portion as a cantilever, this overhanging portion as a cantilever, and you have to find out what is the bending moment at the support C. So you have to find out the moment at C, MC is equal to minus 30 into 2, that is equal to minus 60 kilonewton meter. So here you can find out what is the moment, but here due to this fixed end there is having moment ma, and due to the intermediate support here also having the moment mb. There is two unknowns, so you need two equations so that you can find out these two unknown values, ma and mb. So what you have to do here, at the end a is fixed, so introduce a imaginary span a dash a of 0 length, and a dash is simply supported. Then apply three moment theorem for the span a dash a and ab. Then apply the three moment theorem for the span AB and BC. Apply three moment theorem for the span A dash A and AB, and you get one equation. Then apply three moment theorem for the span AB and BC, and you get another equation. Then by solving these two equations, so you can find out the two unknown value MA and MB. So here introduce the zero span A dash A of length 0, and you have to take the A dash as a simply supported end, and apply the three moment theorem for the span A dash A and AB. As there is no loading on the span A dash A and AB, so here the free BMD, that is capital A1 is 0, and here also there is no free bending moment diagram because there is no loading, so A2 is also equal to 0, and here the small a1, that is the centroidal distance of this free BMD is 0, and here also there is no free bending moment diagram, here also the A2 is equal to 0. So then apply the three moment theorem, that is MA L1 by I1 plus 2MB L1 by I1 plus L2 by I2 plus MC L2 by I2 is equal to minus 6 A1 small a1 by I1 L1 minus 6 A2 small a2 by I2 L2. So apply this three moment theorem for the span A dash A and AB. Here MA is equal to MA dash, and MB is equal to MA, and MC is equal to MB. MA is equal to MA dash and is equal to 0 due to simply supported end. So this is simply supported end. So MA is equal to MA dash is equal to 0, and MB is equal to MA and MC is equal to MB. A1 is equal to 0 and A2 is equal to 0. There is no loading, so the free bending moment diagram is 0. And A1 is 0 and A2 is 0. And L1 is equal to 0 and L2 is equal to 5 meter. L2 is equal to 5 meter. And then moment of inertia I1 is equal to I and I2 is equal to I. Then after putting this value, first equation 2MA plus MB is equal to 0. Then apply three moment theorem for the span AB and BC. For span AB and BC, so here also there is no loading. The free bending moment diagram of this span 0, and the free bending moment diagram of this span is 0. A1 0 and A2 0. And here the MA is equal to MA, MB is equal to MB, and MC is equal to minus 30 into 2. So here you know this moment MC, that is minus 30 into 2, this is equal to minus 60 kilonewton meter. And A1 is 0 and A2 is 0. There is no loading on the span AB and BC. A1 is equal to 0, A2 0, then L1 is equal to 5 meter and L2 is equal to 5 meter. Then after putting this value in the three moment theorem, then you get 5 MA plus 20 MB is equal to 300. So this is the second equation. Then after solving equation 1 and 2, so you get the moment at the support A and at the support B. MA is equal to minus 8.57 kilonewton meter and MB is equal to plus 17.14 kilonewton meter. So here you got this is negative. So for this negative, so the direction is anti-clockwise, and for here at B you got positive value. So here for span AB this is anti-clockwise, and for span BC this is clockwise. For the negative value, so the moment is right side this is clockwise and left side this is anti-clockwise. But for the positive value, right side this is anti-clockwise and left side this is clockwise. So here you got the moment positive, that is mb is equal to plus 17.14 kilonewton meter, and this is the direction of the moment. This is the final bending moment diagram. This is 60 kilonewton meter at the moment at C, and moment at B 17.10 kilonewton meter positive, and moment at A this is 8.57 kilonewton meter negative. This is the bending moment diagram. Then find out the reaction. So by taking the individual span and what is the load is given and what is the moment is due to the load and moments, find out what is the reaction at both end of the span AB and BCD. Let us take for span AB and find out what is the reaction at A and B. Reaction at A is equal to RA and reaction at B is equal to RB1, and the moment here you got this is negative 8.57 kilonewton meter anti-clockwise, and here you got the moment plus 17.14 kilonewton meter, this is anti-clockwise, and for span BCD here this is clockwise 17.14 kilonewton meter, and here the load is given, that is 30 kilonewton meter. First find out the reaction for span AB, RA and RB1. So for span AB, taking moment about B, that is RA into 5 minus 8.57 minus 17.14 is equal to 0. So due to this reaction, the moment is RA into 5 clockwise, and this moment is given anti-clockwise minus 8.57, and here this is also anti-clockwise minus 17.14 is equal to 0. So RA is equal to 5.14 kilonewton. Then take the summation of vertical force is equal to 0. RA plus RB1 is equal to 0. There is no load acting on the span AB. So RB1 is equal to minus 5.14 kilonewton. The reaction is in downward direction. Then take span BCD and find out the reaction at B and reaction at C, RB2 and RC. So first taking the moment about B, RC into 5, this is anti-clockwise, and this is given clockwise minus 17.14, and due to this one clockwise minus 30 into 7. So RC is equal to 45.43 kilonewton. Then take the summation of vertical force is equal to 0. RC plus RB2 is equal to 30. This is upward force and this is downward force. RB2 plus RC is equal to 30 kilonewton. Then RB2 is equal to 30 minus 45.43, that is equal to minus 15.43 kilonewton. So RB2 is equal to minus 15.43 kilonewton. Then you can find out what is the reaction at B. RB is equal to RB1 plus RB2. This is equal to minus 5.14 minus 15.43. This is equal to minus 20.57 kilonewton. The reaction at support A, that is RA, is equal to 5.14 kilonewton, and the reaction at support B is equal to minus 20.57 kilonewton. Reaction at support C is equal to 45.43 kilonewton. Then after knowing the support reactions, then you have to find out what is the shear force at different position of the continuous beam. So shear force at D is equal to FD is equal to plus 30 kilonewton. So at D there is having the downward force 30 kilonewton. So shear force at D is equal to plus 30 kilonewton. Then shear force just right of C. So this is remain constant 30 kilonewton. Then shear force just left of C 30 kilonewton minus RC minus 45.43. That is equal to minus 15.43 kilonewton. Shear force just right of B, this is remain constant. This is minus 15.43 kilonewton. Then shear force just left of B. So here you have to take the reaction RB. So reaction RB is equal to minus 20.57 kilonewton. So plus 20.57. Downward force, this one is downward. So plus 20.57. So this is equal to plus 5.14 kilonewton. Plus 5.14 kilonewton. Then shear force at A is equal to plus 5.14 kilonewton. This is equal to the reaction at T. Then you can draw the shear force diagram. So shear force at D is equal to plus 30 kilonewton. Shear force at C is equal to plus 30. Shear force left of C is equal to minus 15.43 kilonewton. Then shear force just right of B is equal to minus 15.43 kilonewton. Then shear force left of B is equal to plus 5.14 kilonewton. And shear force at A is equal to 5.14 kilonewton. So this is the shear force diagram. So this is positive and this is negative. Now all are clear. How to find out the support moments and the support reactions by using the 3 moment theorem. Then how to draw the bending moment diagram and shear force diagram.